Good afternoon. I welcome you all to our sixth quantum class. So let me start our today's class, which is the sixth of the series. Classes on quantum, PG quantum. So far we have got a lot regarding postulates 1, 2, 3, 4, 5 and sixth one also. And in your syllabus, a line like a few one-dimensional systems is there. Okay. So what I thought that we have learned the postulates. So why don't you continue like using those postulates to understand the one-dimensional systems, or the vice versa. That means using the different one-dimensional systems. Why don't you understand the postulates once again? So that is the first target topic, and then of course we'll go for some other thing like time evolution and conservation laws, constant of motion. So most of the things we have learned are time independent problems, right, in your UG courses as well as in last few days. But today first time we will see something on time dependent, something time evolution and conservation laws. And then we will discuss something very funny and interesting, that a journey if you want to make between quantum and classical. I claim that this is a one-way traffic. What does it mean? One way means you can go from one point to the other, but not the other way from that point to this point. Here the journey which is allowed is quantum to classical, one way, but not the reverse journey, that is from classical to quantum. So I will explain what I mean and what are the evidence, theoretical evidence or experimental evidence that we can justify our claim that it's a one-way traffic. But if it is so, then of course we admit that quantum is a bit superior to classical mechanics, because in special condition you can reach the classical results starting from quantum principles, but not and never starting from classical you can reach the quantum one. So quantum is a more general, I can say, and actually this discussion would be under the title of something that is in your syllabus, which is called Ehrenfest theorem, which is there in your syllabus. So that also we will discuss. So let us start from time evolution and conservation laws, constant of motion. So to start with, again that one-way traffic I was talking about, and some correspondence principle, in the limit of large position and momentum, the quantum results coincide with that of the classical. That means it gives you the classical results also. This is known as correspondence principle. But today we will learn something else also, which is Ehrenfest theorem, to justify the same statement that quantum to classical is a one-way traffic. To be precise, classical versus quantum, if you say, so a special case of quantum is the classical, you can think in that way, where classical deals with something on average, right, a gross mass scale on average, whereas quantum is a very finer something, because it can handle even a single molecule. That means it handles the underlying details of a system, whereas classical gives without bothering about the individual status of the individual molecules. It gives you something gross, and the best example is thermodynamics. It tells a lot about the system's property involving some thermodynamic parameter like Gibbs free energy, Helmholtz free energy, entropy. All are because of the molecules, but thermodynamics never bother about the detailing of the molecules, individual information of the molecules, but still it can give you the good result. So that is classical. But when you come in terms of quantum, then even a single hydrogen atom you can think of, you can deal with, you can evaluate the energies, spectra, etc. So that is a more finer subject, you can say, quantum. One more point, that a classical particle, say M, basically it follows a set of laws which we call Newton's laws or Newtonian laws. Similarly, in quantum, the complete description is given by psi, as we have known in postulate 1, and that psi follows, actually, unlike Newtonian laws, it follows another equation, which is Schrodinger equation. So the question now arises, so parallelly Newton versus Schrodinger, if it is a one-way traffic from quantum to classical is possible, then may we expect equations involving psi that are similar to Newtonian equations? So if you are claiming the superiority of quantum, that it gives you back the classical result, that means in the classical domain it follows the Newtonian equations. So that means starting from psi and psi related equations, you should be able to reach something like Newtonian equations, at least like Newtonian equations, not exactly the Newtonian maybe. So that is the question, and if we can show that yes, it is like that, then we can justify our claim that quantum to classical the journey. So let us focus first at the classical one. It gives you, the momentum. Momentum is mass into velocity. That means velocity is rate of change of displacement with time. That is dr dt in general, or in one dimension you can say px. That is the x directional momentum is mass into x directional velocity. That is dx dt. So that is the classical equation everyone is familiar with since class 7 or maybe even earlier. Another is second law from Newton's law, force. It talks about the force, which is nothing but mass into acceleration. That is the second law of Newton. And acceleration is rate of change of velocity with time. So dv dt, and that is if you multiply m into v, so that gives you p, momentum. So you can say f is dp dt. F is dp dt. So in general and in x direction, fx is dpx dt. So we focus on two equations. One is on involving momentum, this one px m dx dt. Another is involving force, fx is dpx dt. So these are the two equations we are trying to reach starting from something quantum mechanical. So that I will see where from we can do that. In quantum mechanics, of course, we do consider the expectation value, right? When it's not an eigenfunction, then we know how to evaluate the property from postulate 3, that we do the expectation value. So here also, if we think of these two equations, so this quantity would be replaced simply by the average notation, expectation value notation, that is bracket notation. So we are thinking like this. So the first one, px m dx dt, to be replaced by px average, and m is a constant value, so average sign would be here, dx dt, so dx dt. And similarly for the force equation, this should be like this, that if x or average or expectation, then dpx dt, so similarly replaced by ddt of px average. Okay. But one more thing from classical, we know that this is the relation between force and potential energy. If you know, force and potential energy are related by this equation. That is all classical, nothing quantum here. So fx is minus dv dx. So I can replace this fx as minus dv dx. So finally I want dp dx ddt of px and ddt ddx of v minus of ddx of v. That means this one. So either this or that, they are equivalent because of this classical relation. So the equations that are we are interested in is this red color, this one and this one. And now we will show whether we can get it. So let us see. So I have written at the bottom two equations that are target. These are Newton's law, outcome of Newton's law. Now we are starting from something quantum mechanical, and then we will proceed. Let us see where from we start. Let us accept this equation. Later on I will prove that that we start from this quantum mechanical equation. What does it tell? That it's a time average of some of a property omega, whatever it is. So ddt of this omega, that means it is the time evolution, you can say, right, with respect to t, derivative with respect to t. So that left hand side gives you that time evolution or time derivative of some property expectation value, and the right hand side is I by h bar. It's again an expectation value, but expectation of a commutator h comma omega. That means the property you are interested in, that is omega, you have to evaluate the commutator of that property or property operator with Hamiltonian of the system, okay, and that would give you the time derivative of that relevant property. So I repeat, you are interested to find the time evolution of some property ddt of omega. Then first of all you have to evaluate the commutator of that property and the Hamiltonian. So that itself is the operator, and now you take the expectation value calculation of this commutator. That would give you the time derivative of that property. Okay. So this is the starting line of our proof. But later on, if you are interested, of course, we can show this how we can get this relation. But for the time being, let us accept it and proceed. So that is again mentioned. Now you see, an observable that commutes with the Hamiltonian for the system and which therefore has an expectation value that does not change with time is called a constant of the motion, and its expectation value is said to be conserved. That was the heading, constant of motion. So it tells simply that suppose that omega commutes with h. Suppose omega is such a property that the commutator is 0. So the whole right hand side is 0. Okay. And that means also the left hand side is 0. That means the time derivative is 0. That means this expectation of omega does not change with time, right? It's a constant, and derivative of a constant is 0. So if you get the right hand side to be 0, that means the time derivative of that property expectation value is also 0. That means that expectation value of that property does not change with time, and that's why you call it's a constant of the motion. And if it doesn't change with time, then we can say that it is conserved. So other way we can call it conserved property. So that is the quantum mechanical description of something conserved or something called constant of the motion. Now we need the time derivative of here x expectation ddt of delta expectation x, and here ddt of expectation px. Okay, so we need time derivative of this and that. Now time derivative thing is available from here, the left hand side of this equation. That means we want to place this and that as the left hand side of this equation twice, each time. Once this is ddt of x average, and other case it is ddt of px average. So for that purpose, if you want to use this equation, then what we need for this time derivative, it is x. So omega is x. That means you need to evaluate the commutator of h and x. Okay, and for the second part, when the omega is nothing but px, ddt of px, ddt of omega, so omega is px. So for same reason you have to evaluate the commutator of h and px. So here I write that we need for that purpose hx commutator and hpx commutator. So that's a very simple job for BSc student that in fact we have already done in our earlier sessions. So the answers I am directly giving you, that the hx commutator is like this and hpx commutator is like this. Okay, so that you can easily check. You can do it on your own. You please do it later on. Now, so we have got the right hand side. Okay, for each case, one is that h omega, that means hx, and another is h omega hpx. So one by one we will put this result here in this equation. So first let us focus on ddt of x average, that means omega is when x. So I by h bar, and then the expectation on the commutator. So commutator result is this. So that means expectation of this quantity. Now minus I h bar by m is a constant, so it is coming out of in bracket notation. So only px is there. So the expectation of px. Clear? So what I am doing, very simple, I am putting the commutator value here in this equation. Okay. So to get the time derivative of position expectation value. So here after cancellation of h bar, and I into I is I square, that is -1, and minus is already there, so it would become +1, and only only 1 by m would be there, so 1 by m is there, and it is the px average. So we have easily reached just by 2-line calculation, of course after the evaluation of this commutation. So by 2-line calculation we have easily reached what we wanted. You see at the bottom I have already written what I want, that is px average is m cross multiply, so m into dx dt, expectation value. So the first equation we have got very easily. And similarly you can go for the application of the second commutator, this. So in this case your px is the omega, so ddt of omega, that means ddt of px is equal to minus I by h bar, is here, so I by h bar, and from the commutation you get minus h bar by I dv dx, so minus h bar by I dv dx. This is a constant, so it's out of sign. So now if they cancel out h and I, so only minus is left, so the result is minus dv dx. So exactly what we want. Okay, so these two equations are nothing but Newton-like equation, of course with an expectation value, and that is typical quantum signature expectation value. So we have got the Newton's like equations starting from quantum mechanics. So now the question is, where from we get this equation, right, that you have asked. And by the way, these two equations are called nothing but Ehrenfest theorem. So that is in your syllabus, in bold letter it is there, Ehrenfest theorem, and the Ehrenfest theorem are nothing but these two equations. Okay, and their derivation simply this and that. In derivation, two things we have assumed. One is the starting line and another is the commutation value. Out of these two, commutator value that you can easily check, you can do. Maybe in exam you are asked to do, or maybe you are asked to use it only. But anyway, you should be able to carry it out as and when needed. And the second one is this derivation of this. So now let us go to the next slide, where actually as he was asking for the proof, how we can prove. So we can use this time dependent Schrodinger equation. So our starting line actually for that line that we have already used, the starting line is time dependent Schrodinger equation. To derive an explicit expression for the time dependence of the average of an operator, that is ddt of omega, that we are asking for. So start with time dependent Schrodinger equation and then this equation. So the whole mathematical details are there, it's not very difficult, you can easily get it. So finally the left hand side is ddt of a. In case of omega, in place of omega we have used here a in this proof, capital A. So what we get, again you get the commutator of h and a, like h and omega, plus something dA dt. Now but in our starting line dA dt was not there, that means we assume that the property we are interested in, that is omega or capital A, that itself is time independent. If it is so, then it is valid. So if A itself is time independent, then this part is 0. Then we get the formula that we have used. ddt of A average is my I by h bar psi h a psi. So that is the proof, you can easily get it. Okay, you can verify it later on. Now as I have already mentioned, that if this A is something such that A commutes with h, then the whole thing would be 0. So ddt of A is 0, that means A is conserved, that I have already mentioned. But here is a simple but interesting problem, that what about if A is nothing but Hamiltonian itself? Okay, if A, the property you are interested in, that means it was omega initially, now I am calling A. Suppose that omega or A is nothing but Hamiltonian itself. That means the property you are interested in is energy, suppose. Then what happens? Now anything H and the same thing H, they must commute, isn't it? H, H. So you can easily check that H, H commutator is 0. Fine. So if A happens to be H, then obviously this right hand side is 0. That means the left hand side is 0. That means ddt of A, here A is H. So ddt of H is 0. That means energy is constant. Energy is conserved. It's following the constant law of motion. So that is given in this problem, that so that the energy is conserved if the Hamiltonian operator does not depend explicitly on time. So as I assume that A itself doesn't depend on time, then only it is valid. So here again in the question it is mentioned that energy, that means Hamiltonian, if Hamiltonian itself does not depend explicitly on time, then the energy of the system, total energy of the system, is conserved. Okay. So the solution is one line only, that H commutes with itself. So here in this formula you need to replace A by H and self commutator, so it is 0. So equation tells us that ddt of H average is that is ddt is 0. That means it doesn't depend on time. So it's a simple but beautiful problem to demonstrate that why total energy is constant. And we know as stationary state, that is the famous word, stationary state. Why they are called stationary state? Because they don't change with time. Now why they don't change with time? Because of this law of constant of motion. Okay, and because H is a self commutator, HH is 0. Fine. Well, so let us switch over to the next item of our today's discussion, using the postulates to understand the particle in the box and vice versa. So we know a lot about particle in a box, and we have learned a lot about the postulates as well. So today, now I just relate some of the things with some of the problems, and mostly they are given in the problem form, and let us quickly review. Say for example, particle in a box wave function we know in your undergraduate courses, and also the energy expressions we know, and they are quantized because of the n restriction on n. The n has to be integer only, and this is the energy expression for nth level with the length of the box being small a. So at this point we have to make something clear between wave function and eigen function. So wave function means that is a well behaved acceptable function, that is some mathematical property it must have to obey. So if I see S, then it's a wave function. But eigen function, first of all it has to be a wave function, that means all those criteria has to be fulfilled, but moreover it needs to satisfy one more condition, that it has to satisfy the eigenvalue eigenfunction equation like this, SIN equal to SIN. So that means all eigenfunctions are wave functions, but all wave functions may not be eigenfunctions, because if they don't follow this eigenvalue equation, then you cannot call it an eigenfunction of some operator, but of course it can be a wave function. So in the one dimensional particle in box problem, as we know that energy is quantized, and the given form of wave function is actually normalized, and the root over 2 by a is the normalization constant, and the way it is defined, we can easily show the total probability is 1. That means the particle is somewhere in the box. So these are the known concepts we are familiar with. Now we have a problem on postulate 1. So we are trying to relate different postulates with different aspects of the on the box problem. Okay, so the first one is that question, which of the following wave functions are distinguishable from the wave function sin kx? So here are a number of functions are given, wave functions. Okay, but is it distinguishable from another wave function sin kx. That means can we call that the sin kx, the given one, and this question's functions, are they equivalent? Are they distinguishable or indistinguishable? So to look at the screen, you can obviously say, sir, they are not the same. It is simply sin kx, but here all the functions are very different. So how you can say that they are same? I am not talking about the functions are same. I am talking about whether by some suitable consideration, whether they are distinguishable or not on a special ground. So what is that special ground? That we take from postulate 1. That what is the significance of psi, and that we know that mod psi square, that is psi star psi, it is the probability density. So if the probability densities are same of the two functions, then we call that those two functions are equivalent or indistinguishable. So for example, psi 1 is one function and psi 2 is another function. Now what is the probability density? Psi 1 star psi 1 for first function and psi 2 star psi 2 for the second function. Now if these two are same, then we call the functions 1 and 2 are equivalent or indistinguishable. So here psi 2 is say sin kx, so it is given in the problem. So what is psi 2 star psi 2? Sin kx, that means sin square kx. So of this problem, your task is basically to find the product psi star psi of when psi is this or that or that or that. So you start one by one, you take this function as psi 1, you take the complex conjugate of this and then take the product psi 1 star psi 1. Now if it happens to be sin square kx, that is the same as that of the given function, then you can say they are indistinguishable. Apparently it looks very different from the given function, but in fact the answer is all are indistinguishable. So that is given as a task, very simple task. You just take one by one the function, take the complex conjugate and then take the product, and you will see all the results are finally sin square kx as the given product. So the answer is given. Now 1D box we are discussing, so let us focus on the wave functions that we get from solution of Schrodinger equation. This is for the ground state without any node. It looks like this, as you know, and this is for n equal to 30, the 30th state, and this is the n equal to 50. So these are just few examples, and what happens here, that as you go on increasing this quantum number n, the functions looks like this. That means it is almost continuous, no node. So it would be a continuous line kind of thing, and that actually represents something which is related to correspondence principle, that when n is very large, then the quantum gives you the classical results. So here, for example, as far as wave function is concerned, when n is 50, as you see that it is almost continuous, and continuous something is a picture of classical domain, but actually they are quantized in quantum. But if n is too high, then probably we will get the same picture as we get in classical science. So that is correspondence principle, and here just example, another example of this feature. This is in the first one is in terms of wave function, it gets continuous gradually with increasing n. The second one is in terms of energy. Suppose you take the energy difference between two consecutive levels and then take the relative amount, that means dividing by the original En. So En plus 1 minus En, that is the difference between two consecutive energy levels, divided by En, that is the original nth level. So if you put the formula of energy expression once for n plus 1 quantum number and then nth quantum number, and then you divide by the En this expression, then you will on a simple manipulation you will get the result 2n plus 1 by n square. Okay, so I've evaluated a very simple concept, the relative difference of consecutive energy levels. Relative difference. Relative because I am dividing by the energy. So what is the significance? You see that the right hand side result approaches 0 as n tends to infinity. Both the level spacing, the numerator is the spacing, so that is also increasing because n is here and n is increasing. But the denominator is also increasing and it is increasing in a square. So both the level spacing and the energy increase with n, but the energy increases faster, nichetta, the denominator, because it is n square. So making the energy spectrum appear to be continuous. So the relative gap getting lower and lower, and it approaches to 0 as n approaches to infinity, and that means the gap is no more there. If the gap approaches to 0, that means the gap is not there. That means the energies are continuous spectrum, and that is the classical result. So this is correspondence principle in terms of energy. So let me go ahead. The example problem, this is I am giving as a problem. Consider the superposition wave function psi x like this. So if you notice that sin pi x by a actually the first state of the PIB problem, particle in box problem, and there is 2 pi x by a, that means the second state, eigenstate. That means this psi x is a combination of the first and the first excited, I mean ground and the first excited state, right? Combination of these two. Now your task is to find that is this psi x an acceptable wave function for the particle in the box. You know that this individually pi x by a sine and sine 2 pi x by a, they are acceptable because they are already the eigenstate of the particle in box problem. But the question is whether the combination is also acceptable or not. And the next question is psi x is an eigenfunction of the total energy operator H. So these individual functions are of course eigenfunctions of the H operator. But again the same question, whether the combination is it also an eigenfunction of the same operator. And the last question, that if it is normalized or not. If not, then you can normalize, of course, anytime you can normalize any function. This is as a problem, so I am giving you the answers, not the solution. The answer question number A is yes, it's well behaved or acceptable. But the second answer is no, it's not an eigenfunction of H, though the individual functions are eigenfunctions, but the combination is not an eigenfunctions of H. And then what? That we will discuss later. And the third problem is whether it's normalized or not. Again, we can easily show that this function, some constant is there. If you try to normalize, then you will get this constant. Not only that, you will get an extra condition that the C and D, they follow this relation, mod C square plus mod D square equal to 1. So this is the normalization condition that you can get easily. Now the question, another question, that the same function, it's not an eigenfunction of H, then is it an eigenfunction of position operator X? Okay, that's another question. And what is the value of Hx? That we have already used actually in our Ehrenfest theorem. What is the value of Hx? And what do the results signify? So partly the answers like this, that again it is not an eigenfunction of the operator X, that is position operator. Which one? This function, this given function. It's not. You can easily check it. If you operate the operator X on this function, then you will not get it back by constant multiplier. So it's not an eigenfunction. The second one, that Hx we have already used earlier. The significance is that whatever it is not equal to 0. That means they are not commuting. So what do the results signify? It signifies that H and X, that means energy and position, they cannot be determined simultaneously with certainty. So that we know the commutator, how they are related to the uncertainty principle. In the last class we have discussed that. So now However, we can think of average position or probability density at a point and probability over a range of by evaluating proper integral. So that is again connection to postulate 1, that okay, even if the function this psi is not an eigenfunction of position operator, so you cannot get the position eigenvalue because it is not an eigenfunction of position operator, so you cannot get the position value. But then does it anyway give some idea about the position if it's not an eigenfunction? Yes, that is postulate 3, that when the function is not an eigenfunction of the corresponding operator, then of course we can have some idea of that quantity, but in an expectation sense, in an average sense, and that itself is the third postulate, you know. So when it is not an eigenfunction, so that is again mentioned again here, that even if it is not an eigenfunction, no problem, we will go for an averaging. So that is the relation. And again an example problem. It is again related to postulate 1, which tells that mod psi square is the probability density. So here it is given a problem. It is a very popular problem with your undergraduate courses, question papers, that what is the probability P of finding the particle in the central 1/3 of the box if it is in its ground state. So if it's in ground state, central 1/3 means A is the length. So from 1/3 of the length to 2/3 of the length, 2/3 of A and 1/3 of A. And what is psi square psi? Sin square pi x by A, because it is ground state. So sin pi x by A is the function. So taking the square and dx, so multiplied gives you the probability in a small volume. Now if you integrate, you will get the total probability in this given range, which is asked in the question. So if you simply evaluate this integral, you will get 0.609. That means although we cannot predict the outcome of a single measurement, that means third postulate, we can predict that for 60.9% of a large number of individual measurements, the particle is found in the central third of the box. So what is the probability of finding a classical particle in this interval? It would be completely different if you consider the classical. So that is the meaning of this problem, the significance and how it is connected to the postulate. Well, postulate 2 is simply giving you the operator concept, but postulate 3 and 4 are important. So 3 and 4 are the postulates like this. We have already studied a lot. Now you can apply apply Hamiltonian operator on this given function, because it's an eigenfunction of H, so it would give you back always one of the eigenvalue. In this case it is nth, so it would give you En. So that is we also know from the third postulate, that it would give you the eigenvalue if the function is eigenfunction. But what is the fourth postulate? That in the earlier example we have seen that this psi x is not an eigenfunction of H operator. Sorry. Then how we can evaluate the have some idea about the energy? The answer is fourth postulate, that if it is not the eigenfunction, then you have to take the average value by this prescription or mathematical formula. So that we can do. So exactly that we are doing, psi star operator psi dx, right? AJ, psi star operator psi dx, and in the denominator it is psi star psi, but because the function is normalized, so we have not used the denominator part. So if you just evaluate the differentiation first, taking the psi as given, and then you take the integration, then you will find the average like this. So you can please do it on your paper later on, that using this function, given function, and the operator you know here also given, and Vx is for 1D box, Vx is 0, so no problem. So if you evaluate this, the second derivative on this psi, and then you take the integral over the limit 0 to length a, then you will see interestingly the average energy comes like this. So that means it depends on this coefficient C and D. So we can call it an expansion coefficient. That means you are expanding some arbitrary new function in terms of the eigenfunction of the particle in box problems. This is the ground state, this is the first state. Similarly, we can take a few more states. So I can expand this psi like this, and of course which is not an eigenfunction of the H operator, though the individual functions that expanding in terms of which they are eigenfunctions, but the overall function is not eigenfunctions. Then you can take, of course, from fourth postulate the average, and that average would comes as the equation like this. So if you take one more, suppose C, D and F, say F sine 3 pi x by A. So here the result would be plus D square E2 plus F mod F square E3, and similarly mod G square E4 plus dot dot dot. So that is the general prescription. Is very important otherwise. Okay, the way it is there, we can call it a weighted average. So it is just a weighted average, as if you are getting back the eigenvalue of the corresponding expanding wave function component of the expanded function. This E1 is the eigenfunction of this value, this E2 is the eigenfunction of this function. You are getting in the final result of when you are using this combined function, you are getting the result E involving those E1, E2, E3 dot dot dot, but some C square, some D square, some G square, etc. there. So that's why you can call it a weighted average. Okay, so that is how you apply the postulate for a 1D box problem, or other way to apply the 1D box problem to understand in a deeper sense the postulates. So here one of you please read it out for me. Yeah.
Postulate 3 states that in an individual measurement, only one of the eigenvalues of the operator can be measured. In this case, it means that only one of the infinite set of En is a possible result of an individual measurement. What is the likelihood that the value E2 will be measured?
Go on.
Postulate 4 gives a recipe for answering this question. It instructs us to expand the system wave function in the complete set of functions that are the eigenfunctions of the operator of interest. The probability that an individual measurement will give En is given by the square of the expansion coefficient of that eigenfunction in the expression for the wave function.
Thank you. So like this, as I was talking about, that psi x, if you expand in terms of the eigenfunctions of the operator, psi 1, psi 2, they are the eigenfunctions, and C1, C, D are expansion coefficient, and a few more terms you can take, then energy E1, E2, etc. they will be finally in your energy expression, but with this modification, C1, C square, D square, dot dot dot. So that I was explaining here, summarized again. I think the point is clear, isn't it? So the problem looks like this. Suppose that the wave function for a system can be written as expanded. This is C1, D1, etc. C, D, E, these are the coefficient, and phi 1, phi 2, phi 3, they are the eigenfunctions of some operator. Okay. So, and that phi 1, phi 2, phi 3 are normalized eigenfunctions of the operator of energy with eigenvalues E1, 3 E1 and 7 E1. So, it is given in the problem itself that phi 1, phi 2, phi 3, they are eigenfunctions of some operator E hat, whose eigenvalues are E1, the ground state energy, then 3 E1 and then 7 E1. So, eigenvalues are also given. Now, the questions that verify that psi x normalized. So, that first of all the simple task, whether this given function is normalized or not, and then what are the possible values that you could obtain in measuring the kinetic energy on identically prepared systems. What are the possible values? That is postulate 3. If you measure identically prepared systems one by one, then postulate 3 says that you will get one of the eigenfunctions, right? One of the eigenvalues. And then what is the probability of measuring each of these eigenvalues? What is the probability of measuring each of these eigenvalues? So, if you measure then you are sure that one of the eigenvalues will come back, but which one you don't know. That is the fourth postulate. Which one you don't know, but at best you can say on a probabilistic way or an average way. So that is the question, that what is the probability that some E1 or E2, I mean the first one or the second one or the third one corresponding eigenvalue will come back, and finally what is the average value with this expanded expanded function, what is the average value. So these are the few questions exactly relevant to our last 15 minutes discussion. So now let me give you the answer and solution both. First of all, that is the first part is easy, you can check that it is normalized. The second part answer, that what are the possible values? Of course, one of the eigenvalues, that is either E1 or 3E1 or 7E1. And then what are the probability of getting this E1 or 3E1 or 7E1? That means the first, second or third. And as I mentioned, it is the corresponding mod square of the corresponding coefficient. So the first eigenfunction, the corresponding value E1, and the probability that you will get it is square of this coefficient, that is 1/2 square. So this is 1/4. The second one, that eigenvalue is 3E1. That means the eigenvalue this 3E1, the probability of getting it when you measure a number of times, then the probability is of course the mod of this coefficient square. That means 1/4 square, that is 1/16. And here also the mod square of this quantity, mod square, 3 plus root 2i/4 into complex conjugate, so 3 minus root 2i into 4. So if you multiply 3 plus root 2i/4 into 3 minus root 2i/4, you should get 11/16. So I am waiting few seconds. You please, one or two of you, please do it on your script. So thank you. The answer is 11/16. And then the last one, what is the average value finally that you would obtain from a large number of measurements? So average value that I was mentioning, in the earlier slide, this one, C1 C square E1 plus D square E2 plus dot dot dot. So that would exactly happen here. So you have already evaluated the C square, D square and E square. So this square plus this square plus this square. So you have to multiply 1/4 into first level, that is E1, plus 1/16 into second level, that is 3E1, and then 11/16 into the third level, that is 7E1. So that would give the on average energy when you measure with this this function. So please, I am again requesting you to do the calculation, final step calculation. Now we are focusing measurement of momentum or the position. So these are just a few problems, okay. Actually these are all undergraduate level problems, that a function is given to you, the operator is momentum operator is also given, and you have to evaluate the average momentum. So that is the application of the postulate, fourth postulate, that psi star operator psi by psi star psi, because it is normalized, so denominator part is not there. So again, there is an evaluation of this p psi first, and then take the integration, and by a simple manipulation you can show the result is 0. So that means the average position, average momentum is 0. The momentum is mass into velocity, right? The particle is moving, so it is never velocity is 0. So how comes that average momentum is 0? So to start with, the result may look something awkward, something surprising, but actually it's not. How? The answer actually that you know. Anyone please read it out for me, please.
Keep in mind that classically, the particle is bouncing back and forth between the two walls of the one-dimensional box with constant velocity. Therefore, it is equally likely that the particle is moving in the plus x and minus x directions, and that its momentum is positive or negative. For this reason, the average momentum is 0. This result holds up in a quantum mechanical picture. However, a major difference exists between the quantum and classical pictures. In classical mechanics, the magnitude of the momentum of the particle is known to be root over 2m EKIN exactly. In quantum mechanics, a consequence of confining the particle to a box of length a is that an uncertainty has been introduced in its momentum that is proportional to 1 by a. This issue will be discussed.
Encounter this question in UG level, that why, explain qualitatively why the momentum average is to be 0. So classical picture gives you the same result, that it is really 0, but here we get strictly from quantum mechanical calculation, that means the prescription of postulate number 4. Okay, here is again another problem, but this time with position operator. The earlier one was on momentum and this is now position. So again the question is, the function is given and is it an eigenfunction of the position operator? The answer is no, it would not be in the first answer. Solution is given, and then if it is not, then how we can proceed? We can take the average by the same postulate 4 prescription, that means function operator x, then eigenfunction, and then take that integration 0 to a. Okay, so if you did not do all the details of this mathematical part, but the interesting thing is the result is that you will get is a by 2. So length is a and a by 2 is the mid of the length. So that means on average, if you take a number of measurement of this identically prepared system, then you will see the average is coming to be half of the box. When the level is given as the pi x by a, that means the ground state. So if you plot the wave function of the ground state, it will show a maximum at the middle, and that may lead to a conclusion that okay, that's why probably the average is at the middle of the box. No, the peak of the wave function, ground state wave function, is at the middle. That it means the maximum probability for the ground level is the middle of the box, but that doesn't say that on average it will be at the middle of the box. In fact, if you take the second state, right, psi 2, then here 2 pi x by a would be there, and the wave function, if you plot, it will clearly show a node at the middle. So the probability is 0 in fact at the middle, but still on average you get the same answer, a by 2. So they are not the same thing. One is probability maximum, another is average. And on average you are getting the same result because it doesn't depend on energy. It means here the average position is midway in the box. This is exactly what you would expect because the particle is equally likely to be in each half of the box. So if the particle is not biased, then whatever the energy level it corresponds to, it doesn't matter. The particle would try to be equally in left half and equally on the right half. So the average is in the middle. Okay, so that is the qualitative intuitive explanation. But mathematically, if you do this x average with any state n equal to 1, 2, 3, 4, any psi n to get x average n, you will always get the result a by 2 without any n in the final result. That means it is n independent. Okay. Now the free particle, I will not discuss. It is in the PowerPoint presentation. You can consult it later on. It is neither a mention in the syllabus, but I took it as an example of one-dimensional system because it is in syllabus, one-dimensional system. But probably in that line, one-dimensional few systems, they mean only one-dimensional box and probably the one-dimensional simple harmonic oscillator. So free particle part I am just skipping quickly, but the results are there, very sketchy way. So you can just go through these slides, 2 slides only, and you get the important salient features of the free particle case. I'm just quickly skipping these portions, and then we come to the quantum mechanical harmonic oscillator problem. So again, that also is a common popular known problem from your UG course. You know, the SHO means this kind of potential, SHO means this kind of potential. This is the Morse potential, anharmonic potential, and this blue color or purple color is the harmonic potential, and it goes up to infinity. Okay, and also the Schrodinger equation looks like this for SHO system, and the energy, this is the frequency, vibrational frequency, and the energy comes if you solve this Schrodinger equation. Actually, you didn't solve in UG course. Probably you will have some scope in the advanced quantum part when you really need to solve this equation, but right now for our purpose it is neither important the evaluation of this solving this equation, but you just focus on the energy expression that you know from your UG course, that it is h nu n plus half, where this nu is nothing but the vibrational constant, where k is the force constant, mu is the reduced mass. And not only that, you get the energy as well as wave functions, and it consists of some normalization constant and some Hermite polynomial, you know, and some exponential something. And if you just explicitly use the different Hermite polynomial for n equal to 0, 1, 2, etc., then you get exactly these are the wave functions of SHO problem, different levels. Okay, and if you plot along with the potential, then you will see the ground level, that is n equal to 0 level. There is no node here, and then the first level one node is there in between, and then there are two nodes 1 and 2, and there are three nodes 1, 2 and 3, and so on. So with increasing n, the number of nodes are increasing. And one more thing, this color region, different color region, this yellow color, this is classically forbidden region. That means if an infinite potential like this is there, then the classical particle will always be inside this well. It can never go beyond that well because it's infinitely deep, right? You don't have that much of power capacity to jump over the barrier. You cannot. But so that means outside this well, that means the yellow region, you can never be there. That's why you are calling it classically forbidden region. But as you see, the wave function when you plot from minus infinity to plus infinity, that it extends slightly in the yellow region. Of course, it is inside. Mostly it is inside the well, mostly. But a slight portion, if you take the square of the function, probability density, then it will be more clear that a small portion here, 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 here. So small portions is there under the square of the function curve. That means what? It means something very serious. That if the psi square is there, non-zero, that means probability density is there. And that means probability density of what? Of finding the particle. That means even in the yellow region, that is the classically forbidden region, there is some possibility and probability of finding the particle. So this is actually will be discussed in details in the next class, which is also in your syllabus. That is the barrier problem and tunneling problem. So this is in short we call tunneling. That means classically the particle is not supposed to be outside this well, that is in the yellow region, but somehow quantum mechanically it is there, and as if it tunnels through the barrier. It is not jumping over the barrier, but it tunnels through the barrier to go outside the well. So that's why it's called tunneling. And there is a mathematical description. This is a very high level, say the 12th state, the 12th level. If you plot the wave function for the 12th level, then the red colored is the quantum one, having so many of nodes, and the yellow region part is also there, but the blue part is the classical description of possibility or probability of the particle is like this, right? So there are similarity but dissimilarity as well. First of all, in the blue color curve is never in the yellow region because it is classically forbidden, but the red colored is inside the yellow part also. So tunneling is there, and if you increase the number, nth value, 12, 15, 20, 50, then this nodes would be so close to each other that on average it would look like the classical picture. It would look like a classical picture, like a spectrum of the classical. So that means the correspondence principle kind of thing, that when the level is quite high, the energy is quite high, then quantum gives you the classical result. That is another example. So here a few points are mentioned. You just go through, you know all the points actually, that what are the similarities between particle in box and SHO, and what are the dissimilarity. So this I have noted down, and actually in Levine these two paragraphs are there, so you can get it from the PowerPoint file. All the known old things, actually you know what are the similarities and differences between two systems. And then two problems I'd like to give you as task. As I have given for particle in box problems, here we are giving the same kind of problems but for SHO. So for example, I have already given the ground state eigenfunction and the another eigenfunction, and you have to check that they are orthogonal over the interval -2 plus infinity, and also this is normalized over the interval. Of course you need some standard integral and they are provided here. So your job is very simple. You have to evaluate for showing orthogonal, these two functions are orthogonal, you have to take the product of these two and integrate over the given range, and you will get 0 if you use the standard integral. And another is normalization. So if it is normalized, then it should be 1. Yeah, it should be 1. So here you see the result is 1. So you don't need to bother much about these problems, mathematical aspects. To make it, to give you a sense of completeness, actually I am giving these problems. That's why, because in an exam we are not supposed to give this much of mathematical jugglery. Though in undergraduate courses people usually give this type of problems, but I never prefer to give such problems. Rather, my focus is always on the conceptual part, without doing much mathematics in the exam hall, whether you can answer the question from your concepts only. But anyway, that is a different question. So find X average. There's some other problems for harmonic oscillator state and quantum number. Okay, B. So I think qualitatively again you can intuitively again get the answer that position average has to be 0. Position average has to be 0 because the potential midpoint is the x equal to 0. It goes to negative infinity to positive infinity. So the midpoint is 0. So on average, like the particle in box, it was the midpoint of the box. Here also you are getting the midpoint, that is 0. So average position is 0. And for first harmonic oscillator state, the most likely position of the particle. So that is another question, that where actually you have done this in UG levels. What is the maximum probable? What is the position where you can get the maximum probability of finding the particle when the level in the first level, excited level? So what do we do? Suppose that you are given the wave function, so you take the mod psi square, that is the probability density, and then you are asking about where it is maximum. That means it's a maximum minimum problem. That means it is not an integration problem but a differentiation problem. So what we will do, we will take the differentiate del x of this mod psi square and make it equal to 0 and solve it. Then you will get the answer as such. Okay. So these two problems are instructive. You can follow it. And then this is another problem I am not discussing, but it is very interesting that the kinetic energy and potential energy average are same. It was a part of a quiz question actually, you remember. So here the problem is solved, given. So it seems it is already solved in details. I am not discussing. And then another problem, evaluate the average linear momentum of the quantum harmonic oscillator px for the ground state. So I did it for position, now it's for momentum. As exactly I did the pair of problems for PIB problem. Here the same thing we are giving for SHO problems. So initially it was on position, now it's on momentum, px average, and the energy finally comes as, you will get it from here. the last total quantum field. Yeah, that is the last slide I was showing. The n equal to 2 px average, it is not because of integral odd function. Yeah, here is the answer. The px average is again 0 for n equal to 3. You see, px equal to 0 for n equal to 1, px is 0 for n equal to 3, and so on. So it is finally declaring that for all values of n by same argument. So it doesn't depend on whether in which energy level it is, but always the average value would be 0, because it is likely to go in either the positive or negative. So the average would be cancelling out of the positive and negative. They are equally likely. So on cancellation, they give you the final result to be 0. So that's all about today's class. We can have a few more minutes for discussing or having some questions, query on this presentation. Otherwise, we'll make you free.